Welcome to the Weekly Space Hangout for Friday, April 15th, 2016. I'm Fraser Cain, publisher of Universe Today, and with me this week we've got a bunch of regulars and a special guest. So first, regulars, we got Dave Dickinson. David.
Hey, still hanging out here at the Airbnb in Jimeno de la Frontera, Spain for another week.
Right on. Well, thank you for making it. I know it's in the far, far future for you. So
we'll be in Gibraltar next week, so it may or may not be something I can make there. You never know. Hotel Wi-Fi willing.
We got Kimberly Cartier. Kimberly.
Hey, Fraser. Hello, viewers.
Welcome. And we've got Paul, Matt, Sutter. Hey, Paul. How's it going?
Me, reporting for duty. I'm doing pretty good. How are you, Fraser?
Good. And we've got a special guest. We've got Howard Trottier from my home city. Howard.
Pleasure. Thanks for having me on, guys. Looking forward to it.
So you're going to talk to us all about the cool things you're doing up at Simon Fraser University in a second. But before we get into the special guest, I just want to get an update from Paul because he came on the show a couple of weeks ago as our special guest and panelist, and I think you got an update for us.
Yeah, so last time I was on a couple weeks ago, I was all self-promoting a Kickstarter campaign to help fund a film of a dance performance that we're having actually next week, next Thursday, and I'm happy to announce that we made it. We reached our goal. We raised over $25,000. So our live premiere is Thursday night in Columbus, a dance performance themed from astronomy, and we've got a film crew coming out, 5 camera operators, 7 cameras, the whole shebang, so that we can make a professional film out of it and share it with the world. So thank you to everyone who helped support it, and thank you, Fraser, for letting me shamelessly self-promote it.
No, it's good. And you were saying that you got the Weekly Space Hangout bump on the day that you joined us. So
yes,
and that helped put you over the line. So it sounds like it was a very canny move on your part.
Yes, one of the smartest moves I've ever made.
Good. Well, I kicked in, so I'm really looking forward to the final product.
Me too.
So get dancing.
Yeah, I'm not dancing. Don't worry about that. I wouldn't have people pay to watch me dance. But I am narrating, so I've been in rehearsals practicing my narration.
Right on. That's awesome. Well, I think just being able to do these kinds of mixed media kinds of presentations, bringing the science with the art, I think there's a ton of room for that. So I'm really excited. I bet you this is going to be a big thing as you move forward.
Yeah, I really hope so.
Okay, so I want to remind everybody that this is a live interactive experience. We are actually here right now, unless you're watching it on YouTube after the fact, and then we're not. And then what I'm about to say doesn't matter. But what I'm about to say is that you can interact, you can ask questions, you just can join the chat. So if you're watching this on YouTube, there's a chat that's going on. You can pop it out into a special chat where you can just interact with us. We'll be glad to answer questions that you might have for the special guest, or on any of the stories, and we've got some really important stories that have happened this week. So, so stay tuned. All right, let's move on with our interview portion with Howard Trottier, and then we will move on to those big stories. So, once again, Howard, welcome to the Weekly Space Hangout.
Thanks, Fraser. I'm really excited to be here.
So, why don't you give us sort of the quick introduction of who you are and what you do?
Okay, so I'm a professor of physics at Simon Fraser University, which is in a suburb of beautiful Vancouver, British Columbia. And I've been a professor there for about 20 years. So a typical professor, I do teaching, I do research, but the last 5, 6, 7 years I've done something a little bit different, which is to devote most of my time and energy to teaching astronomy and reaching out to the public with astronomy as an example of a science that's excellent for public outreach.
So how are the facilities for astronomy at Simon Fraser University? I mean, it is this wonderful science fiction campus straight out of the future, but or as seen in the 1960s. I've spent a lot of time up at the campus. It's awesome. But how is your astronomy facility?
Well, the thing is, our department of physics is really physics, not an astronomy. We have a couple of cosmologists that do really interesting work. Most universities have an observatory, and actually SFU did not have one until last year. We opened a brand new observatory, which has my family's name on it. My oldest brother and his wife are the donors for it, and so we have a beautiful observatory And actually, it's more than an observatory. It's a public space devoted to science, right smack in the middle of campus. And so it's there as an observatory, but also as a place for people to come and interact with our displays on site.
That's great. And so what are some of the, I guess, the interactions that you've been doing with the public to sort of bring people up into that space and help sort of teach more people's science and physics?
Well, so our astronomy outreach program kind of started as a collaboration between SFU and the local astronomy club, the Vancouver Centre of the Royal Astronomical Society of Canada. We've been doing star parties for years, just out in the field at SFU. But then we have this observatory in the Science Plaza, and we try once a month on average. Our weather kind of sucks here in Vancouver, so when it's clear and it's a weekend, we have the public come out, and typically we have 200 to 300 people show up, mostly young families with young kids that run around looking through not just the observatory telescopes, but amateurs from SFU and from the astronomy club set up telescopes on the plaza outside the observatory. It really is a party. People can look through different telescopes, talk to different astronomers, see our landscape displays. It's really, I think, quite unusual for a university to have this kind of facility.
It is. I do know the weather, and in fact, I don't have a very good telescope because it's sort of pointless to have a really nice telescope here for me on Vancouver Island. You're just a short hop away.
Yeah.
But so what are some of the other what is some of the other research and stuff that's being done as part of your department?
So our department has research in particle physics theory, which is what I do, theoretical particle physics experiment. We have some people who are on the Atlas Canada detector at CERN. We do physics of condensed matter systems, material science, biophysics. So we do a variety of different things, and cosmology. But no observational astronomy as a science. Although our facility is good enough to do science, it's just a question of managing the time for public outreach as well as other things.
I mean, CERN and Atlas. I mean, Atlas is part of the Large Hadron Collider, and
That's
so
right.
and so like many countries in the world, we as Canadians do have a connection to that project. So, what is sort of your involvement in what's going on with the LHC?
So my work as a theorist is really in the theory of the strong interactions, quarks and gluons, and how they're bind together and bound together inside a proton and neutron. And so my work doesn't directly bear on the LHC. It's a different approach to particle physics, where instead of taking particles and smashing them together at very high energies to try to make something new, like the Higgs boson, there are low energy experiments where you do very precise measurements to try to tease out new particles that appear not as real particles, but what we call virtual particles. And so my calculations are on that end of particle physics, the low energy, and looking for signs of new physics and precise experimental measurements.
Yeah, the virtual. I've been sort of doing some writing sort of in this area with these virtual particles. This sort of connected to the Hawking radiation. These are these particles that, when a virtual particle forms right at the event horizon of a black hole. Is this the same virtual particle that we're talking about?
It is. And so, I mean, virtual particles, if you think about empty space as being empty, we've known since Heisenberg and his uncertainty principle in the 1920s that nothing is truly empty. Nature can borrow energy from nothing, create particles, but it has to repay that energy, put it back, so to speak, after a short period of time. So what we think of as a vacuum of empty space is really a seething soup of virtual particles. And we know this to be true. Some of the most precise predictions in all of physical science that have been verified in experiment come from this theory of the quantum behavior of the vacuum.
Right, and I guess in most cases, these virtual particles, as you said, you make them appear, and then you have to give that energy back and reconnect them again. But when you have a special situation, when it's right at the edge of a black hole, in
That's
theory,
right.
Physics is violated, and so the black hole has to pay the price.
Right. So, I mean, loosely speaking, one virtual particle gets out of the event horizon, the other one falls in, and that preserves the overall energy balance. So you don't actually have to pay them back because you have the gravitational field as a source of energy for that type of process.
Yeah. So I'd love to spend a lot of time and talk about what you're doing with Starry Nights, and this is, of course, the astronomy get together. So what days? If you're in the Vancouver area, where can you go and participate in this?
So one of the things about the lousy Vancouver weather is we compensate by scheduling our star parties at the last minute. I might wake up on a Friday morning and it's clear, hey, we're going to go tonight. So we have a mailing list of about 2,000 email addresses, and I just tell people by email in the morning, we're going to have one tonight. Please come if you can. But our site is something very interesting to explore, which can be done day and night, rain or shine. I've got a couple of pictures I'd like to show you just to give you a sense of the
yeah, that'd be great.
Because I think that's really quite special. So let me see if I can do this.
I'm looking at the Trottier Observatory's clear sky chart, and it's looking good for the next little while.
Oh yeah, so next week we're going to be good. So can you see my screen?
Yeah.
Okay, so this is a view of SFU. We're about 20 kilometers east of downtown Vancouver. And that little white square at the bottom corner, that's a grassy field that's been there for 50 years, empty. Now it has our observatory. It's a very, very high-profile location on the campus. So here you can see the site, a view from ground level. At night, it turns into this.
Oh, that's really neat.
So we actually designed the landscaping to talk about the science of astronomy and the beauty of the night sky in different ways. And so those colored lights are there because they represent the spectra of 6 different elements that we chose for various reasons. And so spectroscopy is like the backbone science of astronomy. Without spectroscopy, we know nothing. We have to analyze the light from distant objects to figure out what they're made of. And so that's what this is the sort of architectural backbone of the site, is that plinth that runs up and down the site with those colored lights, which is really quite spectacular at night.
That's wonderful.
And on the right, you see we have 4 illuminated seasonal star charts. You can look at these during the day, but at night they come on, and they give you a very accurate depiction of the night sky. And so those are 2 of the sort of things that you see when you come on site. Different in day, different at night, but always something to look at and to explore. That's
really cool.
Thank you. Yeah, we're very proud of that.
When did this newer facility get completed?
I've got to figure out how to turn off my screen. Oh, there we are. Okay, sorry about that.
Yeah, no problem.
So so we opened in April of last year. This project goes back maybe 7 or 8 years, and around that time, maybe 2007 or 8, I asked my oldest brother, Lauren, who's a successful electronics entrepreneur, if he'd be willing to sort of fund this project. Having a rich brother is very handy when you've got a project like this that you want to build. And my brother and his family, they actually do a lot of philanthropy in science education, so it's a natural fit.
Yeah.
And it took 7 or 8 years to come to the project as you see it now. We went through different changes. Actually, the delays we went through were very good because the project morphed in ways that nobody really anticipated, and it ended up being something very different from what we expected in the beginning, which is this landscape science plaza.
Wow. Next time I'm in the city, I absolutely have to come and check it out. It's beautiful, especially at night. Yeah.
At night is very cool. And then, of course, the observatory, I mean, we have a state-of-the-art telescope with a camera that we can use to do photography. We have a spectroscope that we can use to do measurements. Part of the mandate of the observatory is as student education as well as public outreach. And so we're very big on science-type projects that students can use the observatory to do.
How do you find the response has been from the public?
Very, very good, actually. So the idea of putting this display on this part of the campus, I mean, it's a very high-profile location. As I said, you can't put something there without support of the campus community. So this informal star party that we did for years, it really built a kind of campus support. And we already had many people coming out to our star parties. We had a built-in kind of audience. And since it's opened, we've been, having lots and lots of people come out. Just wish we had better weather so we can do it more often.
Now, with the actual observatory itself, like I know the one that's down by the Space Center, it has public viewing and there's a big lineup and everyone can sort of take their turn to kind of look through the telescope or look at the screen that's attached to the telescope. Is it sort of a similar like that? People can take a look?
It is, and so we do have big lineups, but one of the things that we have is this partnership with the local astronomy club, the Vancouver RASC, and so we'll have 10 or 12 amateur astronomers with portable telescopes set up on the plaza. So you're right, somebody comes in the observatory, they wait for half an hour or longer, they're at the eyepiece for 5 minutes, they bounce out, they have other telescopes to see, they have people to talk to, and so it really makes it, I think, unique. That partnership between SFU and the local astronomers is really, really critical.
How do you find the university? I mean, obviously they've set aside that space, but how do they feel about trying to engage the public in these kinds of activities? Is that a higher priority these days? Because I personally have found that that a lot of people are getting more and more excited about what's going on with astronomy. A lot of it has to do with just the internet and being able to connect with each other and sort of express their enthusiasm. Is that sort of a similar thing you guys are finding there?
We are. And I think one thing I want to say about astronomy, I'm not a professional astronomer. I got into science as an amateur astronomer, and I'm big into it now. Of all the sciences, I think astronomy is very uniquely placed to reach out to the public because it's a visual medium in part. And you look through a telescope, you see nature directly yourself. You don't need somebody to come in between you and that experience. So the idea of getting kids, families, whatever, out to look through a telescope can be a very powerful experience. And so at SFU, the fact that the university gave us this site, we didn't have it in the beginning. We were going to be a building lost on the corner of campus somewhere. The fact that they gave us this location right next to the center of campus was a very big commitment by the university. So this is a high-profile space. People pass by it every day, and it says, science is important. Look at what we're doing here. So I'm very, very excited about that aspect. So lots of support. We had to have it in order to be able to build this thing.
All right, and so once again, if you're in the Vancouver area and you want to participate in this, you want to come and check it out, maybe do one of these live events, what's the best way for people to find out where to go and what to do?
Right, so go to sfu.ca/Starry Nights, or just Google Starry Nights at SFU, and it will pop up, and you get yourself on our mailing list, and you'll hear from me whenever we have one of these events.
Terrific. Now we got a pile of big news, so you were going to maybe stick around, and maybe we'll throw a few comments your way.
Throw me some softballs, that'd be great.
No problem. Well, and once again, thank you so much for joining us today. And I, as a Canadian, as a Vancouverite, I really appreciate these kinds of facilities around the city. I love to see more stuff that the public can get access to that sort of builds their love of science. So I can't wait to see the facility up there. It just looks amazing.
Love to show you, and thanks for having me on. It's a great opportunity.
All right, so let's talk about the giant news, which unfortunately broke literally moments after we finished the Weekly Space Hangout last Friday. In fact, I think a lot of people left our feed so they could go and watch this other thing happen. Paul, what happened?
Yeah, so SpaceX landed part of their rocket on a barge floating in the ocean. And that is kind of a big deal.
Kimberly, you found a video. Did you see if we can try and play that? Well, or you can maybe cue that up, and I'll go to you.
Yeah, let me cue that up for you guys.
Okay. Do you have any more information, Paul?
Yes, so this is their 4th or 5th attempt to do it, and they finally actually did it. It's a big deal for a few reasons. One is we liked the idea of reusable rocket stages, because right now we spend all this money to build a big giant engine and rocket. We launch a teeny tiny thing up into space, and then we just ditch the rest. It's like lighting your car on fire every time you drive it to the grocery store or go to work, kind of costing a lot of money. So there are cheaper ways to do it if we can figure out how to land the first stage or the second stage back down on Earth and polish it up, fill it up again, and then send it back into space or launch something else into space over and over again. And the barge in the ocean part is cool because you can, of course, do this on land where you launch the rocket, in the first stage kind of slows down, turns around, and comes back to the landing spot. But that takes up a lot of fuel, so that limits the kind of stuff you can put into space and how far into orbit you can throw it. But if you have a barge kind of downrange of the rocket, then you don't need to worry about the slowing down and coming back part. You can just lob it up. A little piece detaches, goes off into space, and then the first stage just kind of continues on its path and settles down. And instead of crashing into the ocean, it lands safely on a barge.
The amazing part to me with that landing is how fast it comes in. Kimberly's showing the video right now, and I don't know if you can start it again, Kimberly. But if you watch, this is in slow motion. This isn't even like regular speed, and if you watch, it just comes in so fast.
It came in a angle too. I'm like, when you first look at it.
Yeah, it comes in at an angle, and then clearly some computers just got it all figured out. And
well, if you've ever played that moon landing game,
yeah,
this is the strategy to use. because you don't want to use up all your thrust right away, straightening up.
I'm curious. I haven't heard when SpaceX is going to do a launch featuring a reused booster for the first time. That's probably the next milestone.
Mm-hmm.
Right. And this is, of course, I mean, the other big news that happened this week, although we're not going to cover this, which was that Blue Origins did their third relaunch of the of their booster. Now, of course, it was only to 100 kilometers and then back down. But the fact is,
any kindergartner can do that.
Any kindergarten could do, yeah. But I mean, they have, taken the rocket, refilled it with fuel, launched it again, done it again. So I'm just reading on the chat here. 0xyz abcx0 says the rocket was at an angle because they were fighting the 50-mile-per-hour winds, and yeah, definitely. If you see the waves that were going on, that barge was really dealing with some pretty big weather. So, once again, the fact that the thing just stuck the landing is mind-bending.
Yeah.
Like an Olympic gymnast.
The satellite watchers over in UK had a treat too because they saw the Falcon S2 and Dragon pass over UK about 20 minutes after launch because it was dusk over here. I didn't quite see it because it was north of Spain, but up in UK, a lot of them did see it.
And John Gallant is saying in the chat that the crew gets back on board because it's an uncrewed barge, and then they weld the rocket shoes to the. They've actually welded the rocket to the platform so that it can stick a little better for the return voyage back. And the payload was pretty important too, right? It was carrying a Bigelow Aerospace, among other things. It was carrying this Bigelow Aerospace inflatable. Sorry, what's that?
The bouncy castle.
Yeah, the bouncy castle. Yeah, the Bigelow Aerospace bouncy castle, which
it's an astronaut's birthday.
Yeah, exactly. Time to jump around. So, I don't want to overstate this, but this feels like one of the most important things that's happened in human space exploration in decades. That we are now, thanks to SpaceX, pushing in this whole new range of let's reuse these rockets. As you said, Paul, so we don't have to light our money on fire every time we do a launch. And,
yeah, it's about making access to space cheap, and I think it's one of those things that if you just bring the price down, being the creative kind of people that humans are, we'll think of new things to do in space once it becomes cheap.
Yeah. And then who knows what they're going to use it for. That's not SpaceX's problem. Although we know what they're going to use it for. They're going to use it to send humans to Mars. But this is just phenomenal. And I really look forward to this being a regular circumstance. Just once again, all the time. Oh, yeah, the SpaceX booster lifted off for the 37th time. And launched a bunch of, bricks into orbit because it was cheap. Why not?
As boring as airplane flights.
Yeah, exactly. Yeah, launched garbage to the sun.
Yeah, hopefully they do better than the shuttle with the SRB with usability. They were using them, but of course they had to dredge out of the ocean and clean water out of them and restack the sardine cans, and it was still quite expensive for them to do.
Yeah, about $500 million to $1 billion, depending on the payload and depending on how much refurbishment needed to get done. That is not reusable. That is expensive. Yeah,
because at the beginning of the shuttle program, they said routine like airline flights. It never quite worked out that way with that, but.
And what do we think about the second stage? I mean, now this is old news. This is done all the time. Yawn. So April 2016. Is SpaceX working on that next stage?
No, I've never heard that. That usually re-enters about. Sometimes it makes first orbit. Sometimes it doesn't.
So could it do a full orbit and then re-enter and return to
bring it back? I've never heard them wanting to use the S2. That would be a little more difficult, I would think, but
yeah. Okay, well, so let's move on. So I'm still so excited. John Gallant says that multiple stages are planned in the future. So, yes.
Well, the Falcon 9, that's supposed to have 3, I think, that they want to reuse and fly back all 3 first stage boosters.
Oh, the Falcon Heavy?
The Falcon 9 Heavy, yeah. Exactly.
Yeah. Okay, so let's move on to the next story. And then this is the other big news. Kimberly, we're going to go to Alpha Centauri.
Yeah, apparently we're going to Alpha Centauri sometime within my lifetime, which is not something I ever thought I would say. But earlier this week, the Breakthrough Initiative, which is headed by billionaire Yuri Milner and Stephen Hawking as well, announced that they have a plan to send very tiny, uncrewed spaceships to the stars. And they found a way to do it in only a few decades.
So what's the spaceship going to be like?
The spaceship it's called a star chip, like a microchip, and it's going to make the most out of the new advancements in nanotechnology and be a very, very tiny set of cameras and instruments that only weighs about a few grams. So we're not even talking kilograms here. It's going to be a few grams, and it's going to be attached to a star shield, or a star shade that they plan on propelling by firing 100 gigawatt lasers at the star shield to propel it towards Alpha Centauri at about 20% the speed of light.
Are you just making this up?
I am not making this up. The technology that is needed to create these star chips, most of it is already has been invented, and the stuff that has not been invented yet, like the 100 gigawatt lasers to fire at the very tiny star shields, those are only about a decade or two away. And when Yuri Milner gives $100 million towards the development of that technology, it's definitely very feasible. So I think we're all very excited about it. But you should keep in mind there are still a lot of things, a lot of sort of breakthroughs and troubleshooting that they're going to need to do. First off, how are they going to create this 100 gigawatt laser that's going to fire at a 4-meter star shield in space accurately and not send it tumbling off into who knows where?
Or fry it.
Or fry it. Yeah, even if the shield can reflect 99.999% of the laser light, that's still a tiny fraction of that light that's going to be absorbed, and the material has to not burst into flames when you fire the laser at it. And also, yeah.
Oh, I was
so
going to say,
like the backup plan is we're going to have like a super powerful death ray.
Yes,
so maybe
that is
maybe this is Yuri Milner's. Maybe he is like an evil genius, and he's like, oh, I want to talk to aliens. Oh, I want to send spacecraft, but really he wants to take over the world.
Yeah.
And we're all like helping him.
Yeah, it turns out that super laser gimbals down to go after terrestrial targets as well.
Yeah. Not unless we can direct it pretty. I don't know, but the star shield also has to be strong enough to withstand micrometeorites in the solar system and possibly in interstellar space. We don't quite know what kind of interstellar dust it would encounter.
At what, 20% the speed of
light?
At
20% the speed of light. If it encounters interstellar dust, that would cause a lot of damage to the star shield, and we would need to prevent that.
So after what kind of accelerate it, do you ditch the star shield? Because you just need a quick burst.
I don't think they know that yet.
Okay.
I think they might want to keep the star shield in case they need to re-propel it or recharge the laser and redirect it. I don't think they quite know yet what they're planning on doing with it. There's also the issue of how you're going to get the data back from Alpha Centauri, because if you have such a small spacecraft, you don't have enough room for a power supply large enough to transmit that data back to us. That's another one of the...
That hasn't been figured out?
No, that's one of those hurdles and pieces of technology that they have to figure out.
Right.
So it's all well and good if we get to Alpha Centauri, but we'd like to know what it's like once we're there.
And so whether you send it properly towards Alpha Centauri, whether you immolate your probe, you don't know the difference because there's no way to hear back from it ever again.
Exactly. They do. I see in the chat, Gilad says, "Do they plan to decelerate?" No, they don't. They're planning on a flyby mission. There's no way to decelerate that once it's all the way at Alpha Centauri. But one of the cool things, I think, will be figuring out exactly where the edge of the solar system is, because we don't actually know where the edge of the solar system is. That would be an interesting thing to figure out.
It's weird to me that they sort of came right out of the gate with, like, let's send a probe to Alpha Centauri, as opposed to, like, let's send a probe that can make it to Pluto in 2 weeks.
Right. At 20% the speed of light, you could get there in 2 weeks, and that was part of their, let's put it into perspective, how fast we're going.
I think they do plan to use the same technology to put probes at other planets, explore the moon, Saturn or whatever. So I think that's on the drawing board as well.
Yeah, I think that's part of the draw, is that because it's so small, they're hoping to eventually mass produce these star chips at about the price of the current price of the new iPhone. And so they can mass produce them and launch them in an affordable way. You could essentially seed the solar system and the nearby galaxy with these probes.
So you're saying they're aiming for the stars, but if they fall short, they'll at least touch the moon.
Oh.
Very poetic.
Shoot for the moon, and if you miss,
you land amongst the stars.
Yeah.
If you miss, you vaporize in the atmosphere. Wait.
Yeah.
Wait a minute, that's not how that goes.
I don't remember.
We should be on the lookout for alien star chips in our own solar system.
Well, that's the thing, right? Where are the aliens? Where are their starships? Why aren't we seeing those?
Well, we probably wouldn't notice them if they were that tiny.
I thought we were going to talk aliens.
I thought we put a kibosh on that for this week.
We're not talking about megastructures, but we will always be talking about aliens.
Microstructures.
Alien microstructures. That's exactly right.
Kimberly mentioned a number of the technical challenges. There are others, like this 100 gigawatt laser. It has to be like spread out over a kilometer in diameter, so that the laser beam can be avoid what's called the diffraction limit, or diffraction limited resolution of the laser beam is of the right size to power the spacecraft. They have to compensate for distortions by the atmosphere, and some of those technologies are there, but not nearly at that scale, from what I understand. It's like the technological challenges, as Kimberly said, are huge, and maybe shouldn't be underestimated.
Yeah, right now they're planning on building that laser right on the ground, mostly because it'll be about 50 times cheaper than trying to build it in space. But you introduce a whole new host of problems when you have to send a powerful laser beam through the atmosphere.
Definitely.
Why did Stephen Hawking kind of jump on board this one?
Stephen Hawking's been on board with other parts of the Breakthrough Initiative as well, like the recent Breakthrough SETI initiative, which is Breakthrough Listen, if I'm not mistaken. Stephen Hawking was on board with that one as well. And with the breakthrough prizes, he's sort of been on board with all of your.
I think he's literally on the board. The breakthrough.
Okay.
He's on board because he's on the board. I got it.
Because he's Stephen Hawking.
Yeah. What kind of interstellar debris would they be looking at? What kinds of particles and stuff do you think, Howard? This is a particle physics question. What kind of stuff is out there in the region between us and, say, the nearest Alpha Centauri?
Darn good question. I guess it's particles of dust that are the primary worry. I don't know a whole lot about the interstellar medium. It's very, very, very thin. So I think my understanding is the chances of a collision with a dust particle are very, very small. And part of the idea is they have lots and lots of these micro vessels out there. So if one gets destroyed, the others continue on.
But isn't it like bordering on a particle accelerator? I mean, if you're smashing particles in at 20% the speed of light.
Definitely, one of these microscopic particles, I think, the impact at that speed would obliterate the device completely.
And we've also got cosmic rays to worry about. There's lots of extragalactic cosmic rays that were protected from by the cosmic rays produced by our own sun, that provides kind of like a little safety bubble around us. But once you leave the heliopause and you're truly in interstellar space, there's a very high, relatively high density of just high energy particles that are just slamming all around. If that doesn't fry your little micro spaceship, it's certainly going to potentially deflect it.
Right.
I imagine decelerating once you get to Alpha Centauri is going to be out of the question too. So it's
that's impossible. I mean, I think the virtue of the spacecraft is it's very, very small, so the area that it presents the cosmic rays or dust particles is tiny. So I'm not sure they know enough about the density of the medium and the components of these cosmic rays to know for sure. But they're small. So
maybe they can aerobrake.
Cosmo break.
Cosmo break. Like just dip into the atmosphere of the sun when it gets there, and then use that to break. Well, this is great. I think aim, as you said, Paul, aim for the stars, and maybe instead what we'll get is something that'll allow us to send spacecraft to the moon. In an hour, which would be still very handy.
And we still have the giant death ray.
And we still have the giant death ray.
It's a win all around.
Yeah. When anyone questions his plans, he just scorches that part of the plan. Right on. All right, Dave Dickinson, let's talk about a fairly rare event that's coming up, a transit of Mercury.
Yeah, Bob King just put an article about this earlier today, about the upcoming transit of Mercury on May 9th in front of the sun from our earthly vantage point. And me and Bob actually kind of teamed up on this and talked about who was going to write about what, and I agreed that he could have the transit of Mercury if I get the opposition of Mars, which is coming up next month as well. But I did also write about the prelude to the transit leading up to this week's or next month's transit of Mercury. As you can see Mercury in the evening sky right now, very low in the dusk. The moon was next to it last weekend, which made a good guide point to see it. But if you've never seen Mercury, it's down below, kind of forms a right triangle with Aldebaran and Taurus and Capella up in Auriga. It's right down below that, so it's kind of easy to see. The transit on May 9th is going to be about 7 hours long. If anybody remembers the transit of Venus back in 2012. However, transits of Mercury are much more common, roughly about once a decade. The last one was 2006, and I was courting heat stroke out in front of the Trottier Observatory, showing people the transit of Mercury in Arizona back then. That was just about before I actually started my blog, like a few months prior to that. And there's another one in 2019, and I don't think there's another one till the 2030s. There's like 11 transits this century. Mercury transits the face of the sun more often than Venus because it's in closer, and it shows it has a larger chord of its orbit that can be seen to transit from Earth. So it's kind of an interesting thing to see. They used to use these transits back, when I talked about during the transit of Venus. As a matter of fact, that was right before I started writing for Universe Today when that happened. But that was, they used to use these way back in the day to try to gain the measurement of the parallax for the scale of the solar system, and it used to serve a crucial scientific purpose. So it's kind of interesting to watch these.
Now, with the transit, this is something that anyone can watch if you don't need a very complicated setup, right?
No, you could. Mercury's a little smaller disk-wise. It's like 7 arc seconds, I believe, in size. So it's going to be teeny. It'll look like a tiny black dot, like a sunspot on the sun. But you can see it if you have a decent projector system. Like I've used binoculars on tripod to project it back on a piece of cardboard or white paper. Just make sure you got a big enough disk and you don't accidentally set the paper on fire with binoculars if you get it focused up too close.
And you got to be careful not to melt out the optics of your binoculars. So I've done that with a spotting telescope. I left it.
Oh wow.
Yeah, well, I left the telescope pointing in the direction of the sun, and I was able to see a partial solar eclipse. And I just left it there for the next day, and so it caught the sun the next day, and just sat baking in the sun for a couple of hours.
There was an amateur astronomer a few years ago. I think it was in Minnesota. He actually did set a small fire on his porch with his Dobsonian because he just left it out uncovered, and the sun just happened to angle right through the eyepiece. It focused onto a piece of wood on his deck, and it actually caught fire. So I have heard of that happening. Yeah. I know Schmidt-Cassegrain telescopes, because they got folded optics, you don't want to aim those at the sun because the heat can really build up in the tube. Usually the long refractor ones, again for projection, are fine. But you could use solar glasses. You could probably see the transit of Mercury. You could use a hydrogen alpha scope. I don't have mine with me right now, but anything with the proper filter on it, you could use.
Could you resolve it with your eyeballs if you were looking just with solar glasses?
I think it would be difficult. 7 arc seconds, actually, I want to say. I know Venus you could. With the solar.
I'm sorry to interject, Dave. The eye's limitation is about an arc minute, about 60 arc seconds. So I think it would be impossible.
It'd probably be kind of difficult to. Yeah, I know Venus you could, but Venus is pretty close to that when it's a solar conjunction. But Mercury's, like I said, 7 arc seconds is kind of tiny.
Howard, do you guys have any plans to try and observe it?
So actually, we'll get together with our local partners at the Astronomy Club to do something. They have solar telescopes. We actually don't have one, and so our scope is really not suitable for looking at the sun. One thing that always kind of spooks me a little bit about doing public events is you see a kid see somebody looking through a telescope with a solar filter, not knowing that the filter is there. It's like really dangerous. So I walk around warning people, don't do this with just an ordinary telescope or binoculars. You'll go blind in an instant.
Yeah, absolutely.
Vancouver, you guys get it at sunrise there. Here in Spain, in Western Europe, in Eastern North America, we're going to see the entire transit. And then east of us here, like in Eastern Europe and Israel and the Middle East, they're going to see it at sunset. So. Right.
Paul, let's talk about a dark matter-dominated dwarf galaxy.
Yeah, so ALMA, the radio telescope in Chile, took this very, very cool image of a rather large galaxy, and then behind that was a smaller galaxy that got lensed around it, gravitational lensing, and using a bunch of supercomputers and some math and some science or whatever, they were able to reconstruct the distribution of stuff in that galaxy that's between us and the very distant galaxy. And they found a little surprise that there was a clump of matter that was not lighting up. It didn't have its own stars, it didn't have its own hot gas, but it was affecting the lensing structure of the galaxy behind it. And it's a dwarf galaxy and dominated by dark matter because it's not glowing, otherwise it'd just be normal matter. So it's dark matter, and this is cool because lensing, gravitational lensing, is a way that we can study the dark matter structure of objects, because dark matter feeds into the general relativity equations for lensing, just like normal matter does. And one of the big questions in cosmology is, when we do simulations of the formation of structure, the formation of galaxies, when we do generic simulations with dark matter in it, there tend to be a lot of small dwarf galaxies that orbit normal galaxies like the Milky Way galaxy. And then when we look out with our telescopes, we kind of don't see as many as we expect. So there used to be this really large discrepancy, and that posed a potential problem for standard dark matter cosmology. But over the past 10, 15 years, that difference is coming down, one, because we're doing more sophisticated simulations where we're figuring out, okay, maybe there weren't as many small dwarf satellite galaxies as we originally predicted. And then as we're doing more sophisticated observations, we're picking out really dim structures, we're picking out really dim dwarf galaxies, and so our counts of the number of dwarf satellite galaxies around all the big galaxies is coming up, but there's still a little bit of difference left over. And the last thing we're thinking of is that maybe there are small dwarf satellite galaxies that are pretty much all dark matter. They just never got enough gas to light up in stars, and the only way to detect these is through lensing. The only way to detect them is through ways that don't depend on light. So here's one case of ALMA finding one of these dark matter dominated satellite dwarf galaxies, and this kind of lays out a future program of maybe we can start doing surveys with this, we can start to map out, get lots of dwarf galaxies, and see if our predictions from our simulations, from our theory, are right after all.
So does this give us, a much firmer indication on what dark matter is?
It potentially can if we're able to figure out the structure of these dark matter dwarf galaxies. If we can figure out the density, if it's really dense in the center or just a little bit dense in the center, maybe it's smooth out. By looking at the detailed structure, that does provide some clues about the nature of dark matter, how well it, say, scatters off itself or interacts with itself. That affects some of these detailed things, but that's probably outside the range of what we're capable right now.
So do you think that there's a lot of these out there? I mean, could this account for some of that missing mass that we thought had been figured out, and now it hasn't been figured out?
There is definitely a sense that there's a lot more what we call substructure in the universe than we had originally assumed, and that's simply because you need a lot of dark matter piled up to attract a lot of gas, and for that gas to light up in stars. And if you're just looking for the stars, you're just going to miss a lot of these blobs of dark matter. They're just hanging around, orbiting the big galaxies. And with more sophisticated observing techniques, especially through lensing, we will start to pick up more of these dwarf satellite galaxies that just don't light up.
Would it fill the sort of that missing mass, or is it still?
That's an open question. We might. Right now, it's off by a factor of 2 or 3 between the predictions and the current count of typical numbers of dwarf satellite galaxies. Maybe it's enough, maybe not.
Well, it'd be nice. I mean, the poor researchers could really use a break.
Yes.
Because they had that so cruelly taken away from them. All right. Kimberly, let's talk about some good news about Kepler after the bad news.
After the bad news. Well, the bad news was late last week, Kepler scientists tried to communicate with the Kepler satellite, which was about to enter its 9th campaign in its K2 mission, and found that the spacecraft had put itself into emergency mode, which it had never, ever done before in its 7-year lifetime. And they spent the next few days, all weekend, trying to get the spacecraft back from emergency mode in time so it could start its Campaign 9 observations of the center of the galaxy. And on Monday, they finally got a response from the spacecraft and were able to recover it from emergency mode, which only put it a few days behind schedule. So that was a sort of a whew. Luckily, we avoided that catastrophe. They still have no idea why the spacecraft went into emergency mode in the first place. Emergency mode automatically triggers because of any number of spacecraft potential malfunctions. It's sort of a safe mode so that something catastrophic doesn't happen. And anything can trigger it, and they haven't been able to figure out why yet. They're still looking into it. But luckily, they were able to get it back, and they only lost a few days of observations in this campaign. Now, Campaign 9 is particularly exciting and important because it's staring at the center of the Milky Way, and it's undergoing a microlensing campaign, searching for planets via microlensing, sort of like Paul was just talking about with gravitational lensing, but on a smaller scale to search for planets. In particular, they want to find free-floating planets that are not attached to any stars, and microlensing is the only way to do it. And so K2 was anticipating finding around 10 free-floating planets during the 80 days of Campaign 9, and so they were really scared when they lost the first few days because this would be their only chance to do this type of observation.
Is there, I mean, that whole idea, right? So you could have planets that just formed all on their own out of some smaller piece of a nebula, but they weren't actually attached to some star, or maybe ejected from some other star system in the turbulent area close to the core of the Milky Way?
More likely the planets were ejected from their solar system because it's very difficult to take a nebulous gas cloud and have it condense all the way down to such a small, compact object on its own. That's a very difficult thing to do. And usually you can only get down to sort of like medium-sized brown dwarfs, which are about a tenth of the size of the sun or so. And that's about the limit that you can do that for. So usually ejected planets are what we're looking at. In And Campaign 9 was
believe
also...
I may be wrong, but I think the current model of the solar system formation is we lost a planet early on too, and I think it's just fairly typical in any solar system formation. You're going to lose a couple.
Right. Actually, these all these hot Jupiters that were discovered, they were sort of a mystery at first. Nobody really anticipated them, and they probably migrate inwards by ejecting other planetary bodies out of their solar systems. You know, they end up like up close and personal with their parent stars. So that strongly suggests, I think, that you're going to find lots of free floaters.
Yeah, definitely.
Very cool. Well, I'm glad it was sort of rescued. I mean, I sort of feel like we're living on borrowed time with Kepler at this point.
I feel like we are too, and I think we should be really grateful that we've gotten all the way to Campaign 9 of K2. And actually, something really interesting I learned about Campaign 9 just earlier today is that they're actually teaming up with a bunch of amateur astronomers on the ground for their microlensing campaign, because you need to observe the microlensing event both from space and the ground to get the proper trajectory, to get the distance to that microlensing object. And so there's actually a website called ExoFOP, where amateur astronomers can coordinate with the Kepler team to observe the same microlensing events at the same time. So I'm really glad that they were able to get the spacecraft back in time for Campaign 9 to go forward, so that all of the amateur astronomers can participate as well.
It's mind-bending that an amateur astronomer with a backyard telescope can participate in confirming a planet that's, you know, near the core of the galaxy, whatever, 20,000 light years away. It just blows your mind. But
that's very exciting.
Very exciting. I had no idea. I'm going to get on it right away.
So if you have a backyard telescope and you want to help confirm planets, go look at ExoFOP. That's ExoFOP. So.
Yeah, amateur astronomers play a big role in confirming these microlensing events, and because of the way the physics work, you can not only you can detect the star, the planet lining up, just with incredible precision. The downside is you only get one shot at it. You never get a chance to detect another one. So.
Yeah, that's why as soon as either someone on the ground or the Kepler team spots the beginning of the microlensing event, there's going to be a massive coordination effort to get everyone's telescope pointed at it all at the same time, because you get one shot and one shot only.
Dave Dickinson, let's talk about that really big sunspot that's on the sun.
Yeah, this started about last Sunday night or so. I started seeing images of this enormous sunspot coming around the solar limb, and it just passed about mid-transit on the disk, and now it's starting to rotate away from us. And it actually was kind of funny. There's a little bit of pareidolia going on earlier this week. It actually had a heart-shaped appearance for a time. They're right about as it was aimed at the Earth, which was kind of funny. But it was this is the largest sunspot we've seen in 2016 so far. And it's strange because the week before that we were discussing about how it seemed like we were going toward a spotless stretch right now where there was almost no solar activity, and we were on the backside of cycle 24 right now, and it seemed like we were going back toward, remember in 2009 we had like one of the deepest minimums in a century where the sun was showing almost no sunspots for a good majority of the year back in 2009, and it seems like we're going back toward another spotless stretch again, but it just shows that the cycle 24 still has a few surprises in store. This one didn't throw any solar flares or CMEs at us, surprisingly, but it was kind of interesting to see, and it's still there on the sun if you have a solar scope or a solar filter. You can see, some amateurs were telling me that they could see this one using just solar glasses and no magnification, that it was large enough to see without having to use any magnification. So
yeah, one astronomer that I like, Shahrin Ahmed out of Malaysia. Yeah. Shahgazer is his handle. Took a bunch of really great pictures of it. Also, the upside down astronomer Paul Stewart out of New Zealand, and it totally looks like a heart. It's hilarious. The sun loves us with it.
Apparently.
Yeah, but it's funny. I mean, do you remember back in 2009, 2010, as we were leading up to the peak on cycle 24, and the conspiracy nuts were absolutely certain that this was going to be the one that was going to scour the planet of life?
Well, there's a lot of discussion with the solar helioseismologists. There's one I interviewed. They were talking about, there's some discussion that cycle 25, we're kind of in a larger cycle where they seem to be getting weaker and weaker, that cycle 25 may be absent altogether. There's some discussion about that right now because the solar cycles through the 70s and 80s were much more intense than what we're getting now. And there are some ideas that in addition to that 11-year cycle that we get, that there may be larger cycles that we just haven't really defined yet, that the sun goes through over a span of a century or many centuries or so. So it'll be interesting to see. Now we have SDO up there and SOHO and Hinode and Proba-B and all these other solar observatories, the stereo A and B. So we're going to be able to, cycle 24 was the most steadied cycle of history, and we're just going to continue that because we really need to. The sun, more than any other astronomical object, really impacts life here on Earth and what in our society. So.
Paul, we got time for one last story about dust from beyond the solar system.
Yeah, so Cassini, orbiting Saturn, collects dust grains, and most of those dust grains are from our own solar system, just floating around. But every once in a while, they get a dust grain that has a really high velocity, and it's coming from kind of a weird direction. And so far they've collected around 36 or 38 of these dust grains. And they think these dust grains, because of their speed, because of their weird direction, are actually coming from interstellar space. And they've analyzed these dust grains. They have different levels of radioactive isotopes than the dust grains found in our own solar system, a slightly different mix, typical mix of elements and metals than what the dust grains we have in our own solar system. So that is also evidence for the fact that these are not coming from our own home. They're coming from somewhere else. And researchers are very interested in these dust grains because they give us clues about what the environment is like outside of our own little bubble, outside of our own little solar system.
It's pretty exciting. I mean, as we look at all of the rocks and asteroids and meteorites and everything we see, it was all formed the same time as part of the solar nebula, and so you just can't get that time dating for anything else. But
exactly.
And so if we can do that, then we can start to see what the rest of the Milky Way is made out of, and not necessarily, and how similar the stuff is. Where do these grains come from? Were they ejected from other star systems? Were they just...
Yeah, we think they might be ejected from other star systems, maybe distant supernova remnants, just finally now passing by the solar system and through the solar system, or just hanging out in space. There's lots of junk out there. Or maybe they are disintegrated alien microprobes. Right. Come to explore this strange yellow star, or excuse me, white star, and didn't quite make it because of all the cosmic rays.
Yeah, this is what's left after that long journey, is one tiny little piece of dust, that's been just smashed so many times. It's a terrible idea. Don't send the spacecraft that quickly. All right, well, I think we've reached the end of the show. Let's wrap things up. But before we do, I just want to once again, as always, give a big thanks to the WSH crew. This is the people who... my computer is beeping. The WSH crew, these are the people who really act as the producers of our show. They're the ones who sort of talk about this. They organize our special guests, and they talk about the show, and they really fill our chat with all kinds of goodness. So if you want to be a part of that community, I highly recommend just do a search for the WSH crew. They've got a website now. They've got a community on Google+. We've got all kinds of great places they communicate, and I'm not kidding. They are the producers of this show. They're the ones who who organized this week's special guest and many of the other special guests, and you should see the list of upcoming guests. So if you want to really control how this show works, join that community. All right, so let's go round robin here. Dave Dickinson, where do people find out more?
Yes, I'm at AstroGuys with a Z on Twitter. I have blog AstroGuys. I write for Sky and Telescope, Universe Today, List to Soar, and documenting my travels on Instagram, on AstroGuys, and also next week is the mini moon, the smallest full moon of the year, so we'll be writing about that again, patented on Universe Today. So
let's get that name to stick.
There you go.
Kimberly, where do people find out more?
People can find out more by following me on Twitter at AstroKimCartier, by checking out my website, kimberlycartier.org, And if you happen to be in the region of Buffalo, New York tomorrow evening, I will be giving a talk for the Buffalo Astronomical Association for their annual banquet. So come on by and say hello.
And what research are you working on right now, if you could talk about it?
Right now, I am working on studying the atmosphere of a hot Jupiter exoplanet to determine whether there is water or other fun molecules in the atmosphere.
Well, please let us know when you find out.
I will let you know when I have more.
All right. Paul, where do people find out more?
They can follow me on Twitter and Facebook at Paul Matt Sutter. You can also listen to my very own podcast after you're done listening to all of Fraser Cain's podcasts and shows. You can go to askaspaceman.com, listen to my own show, and also realspacepodcast.com, where I interview other scientists and educators and communicators and whatnot. To support those shows, I have a Patreon campaign, patreon.com/PMSutter, that helps pay for the shows. And if you're in Columbus, April 21st, Thursday night, 7:30 p.m., come on down to the Capitol Theater for the live premiere of Song of the Stars.
Yeah, if people want to experience your science through the medium of dance, this is how they do it.
That's the place to do it. Yep.
Yeah. Yeah, I want to have science danced at me.
In your face.
In your face. All right. And our special guest, Howard, once again, thanks for joining us one last time for people who want to find out more.
Sure. Thanks, Fraser, again for having me. So it's my Twitter handle is Mr. Starry Nights, and our website is sfu.ca/Starry Nights, one word.
Wonderful. Okay, great. And once again, I'm Fraser Cain, FCain on Twitter. We've got lots of great space guide to space videos coming out for you. What did we just do? How long does it take to get to Jupiter? Are there storms on the moon? We've got what's outside the universe. That's coming next. And then we're going to be talking about Planet 9, and I think we're going to do a video on the Starshot mission. So make sure, if you haven't already, click subscribe. And like, we're at 74,700 and something. So you know,
Ooh.
Let's get to the 75,000 mark. That's really all I want.
Tell your friends.
Yeah, exactly. And your enemies. Make them all join. Well, once again, thanks everyone for watching. Thanks to the astronomers for joining us. Thanks to our special guest. And we will see you all next week. One last piece of news. We're going to be recording Astronomy Cast at a very special time today in about 3.5 hours. So if you normally expect your Astronomy Cast on Mondays, it's happening today, which I know our Australian and New Zealand fans appreciate, that they can actually watch it. So Astronomy Cast live in just a few hours. All right. You can find information on the Astronomy Cast page. All right. Thanks, everyone. We'll see you all next week.
See ya.
Yeah.